Thanks a lot for being here today. I know this is a very dry and abstruse topic, but it's one I care about very much, so I appreciate that hopefully some of you do too. This is a talk about sharding, clearly. I am Adam Mckaig, and I work on the online databases team at Stripe, like we just heard. We run a multi-petabyte Mongo cluster at 5 nines of availability, which is a very interesting thing to do. However, we don't have distinct dev and SRE roles at Stripe, so I'm not actually technically an SRE. We do carry the pager for our service, and for the decade or so prior to this, I was an SRE at Datadog, at Google, and at the New York Times. So I hope that you can forgive me for not being an SRE and listening to me anyway. To clarify, this is not a talk about Stripe, per se. I'm just borrowing a lot of the interesting stuff that we've learned at Stripe and sort of presenting it to you. But I'm also borrowing a lot of the interesting stuff that I learned at Datadog and a lot of the stuff that I learned at Google, etc. Which is why I'm using the default Google Slides template for these and not Stripe's beautiful designed slide deck. So the reason I'm doing this talk and telling this to you is that over the years, I've noticed that like variations of the same problem, they keep on coming up over and over again. They're all different, like every single problem is a little bit different, but when I look at it, when I think back, the core of so many of them is basically a workload sharding problem. So I'm trying to share like what I learned in solving a lot of those problems over the years. So hopefully we can try and standardize some of these solutions, or at least standardize the problems, the way that we talk about them, so we can focus on sort of the more interesting part of the individual problems, which is what makes them different. Now, my goal isn't to like define, over here B is like great sharding, everything's good, and over here A is sort of where you are. If you could define B in advance, which you can't just stop what you're doing and go and build B. It takes years. You don't even really know where the destination is. In reality, there are actually a million intermediate steps. All of us are somewhere on this like imaginary map of where our sharding is today. We're over here, the destination where everything is great is there, and there are so many different steps in the middle. So if you have a crystal ball, you can take a pretty efficient path from A to B over the years. If you know exactly where you're going, then you can keep on moving, taking small incremental steps while moving towards the destination, which is, again, great sharding. And a lot of companies, I think Google coined this term, a lot of companies call these roof shots, which is like a small moonshot. So it doesn't really matter if it fails or if it goes wrong, it's inconvenient, but it's not the end of the world because it's quite small. Going straight from A to B, on the other hand, would be a moonshot, and it would be catastrophic if it failed. So generally speaking, we try not to do those. So the efficient path is not the only path that you can take. In fact, to be honest, like every company that I've worked for takes this path, not the efficient path. Like we're all just kind of stumbling around, trying to figure out like what should our sharding look like, and then we take a wrong turn and we have to overcorrect a little bit. That's okay. Probably a lot of you are on this journey too. My goal in a lot of ways is to try and straighten out this curve so we can maybe save a little bit of time. But the main thing is to avoid this, which is where you spend a little bit of time going down individual paths, say, well, you know, our shards are on fire, so we've got to advance a little bit. You do something incremental, and then you realize like, oh shit, like I'm out of options. I don't know, and you'll note on my little like imaginary diagram here that where you are now is actually quite far away from the next nodes. You've got to now take a big step to get yourself back on course. We call these trapdoor decisions at Stripe, and we try and avoid them like the plague, because it's one thing to incrementally move in the wrong direction, but it's another thing to like have to course correct in a big way. We try and avoid that. So here's the agenda of this talk. First, I'm going to talk about some of the problems that you might encounter as your system grows in like various dimensions. When you see these problems, light bulbs should go on. Maybe you think, this is another bloody sharding problem. I heard a little bit about that, because that's what I try to do. Second, I'm going to show in practice like how this basically works. How taking an unsharded system and making it sharded works. Now, a lot of the time you'll have systems that take care of this for you, but it's really important in my experience to understand what's happening behind the scenes. Third, I'm going to enumerate some of the patterns that I personally think about at a quite abstract level when I'm confronted with these problems, like how am I going to slice up this workload in the simplest and sort of most abstract form that I can. And then fourth, I'm going to talk about what I think of as a paved road. Like I've taken that path through all of those intermediate dots like quite a few times now, and there are some waypoints along the way that I can categorically tell you not to do. Others, it depends a little bit more. But I'm going to try and present what I think of as like the default path through here, which is not to say you should never take any other path, but you should think about why you're doing that. You should have a good reason for taking a separate path. Now, before we get started and talk about details, I want to talk about the first rule of sharding, which is don't. I've seen so many systems over the years which are sharded sort of preemptively, and then they turn out not to be. Now, sharding is complicated. It is almost always more expensive than running an unsharded system. In many cases, it's a lot slower. It has fewer capabilities than an unsharded system, so don't. Use sharded systems when you have to, not like proactively. Now, the second rule of all of this is to have a plan. It's to be prepared, it's to think ahead. You don't obviously want to think too many steps ahead, but you've got to bear in mind, I've painted myself into a corner so many times with this. How am I going to split up this workload? Like, what am I going to do when I need to shard it? Don't overthink it, but like, do think ahead a little bit. Otherwise, you're going to end up in that third situation without a lot of options. So before we start, let me just define exactly what I mean by sharding. This will only take a second. So we've got a workload, right? Like all of the requests which are coming into your system. This is all of it. This is, of course, made up of a lot of smaller requests which are coming in. Some of them are big, some of them are small, but they all comprise like the overall workload. Sharding is basically the process of taking this overall workload and breaking it down into smaller workloads. Now, exactly how you do that, I'll get into in a second, but it's subdividing workloads into smaller workloads so that they can be processed by separate machines, basically. Now, I've drawn little databases here, but this applies to stateless workers just as much as it does for stateful workers, although the latter is a little bit more complex. So here are some problems. A lot of them have sharding-shaped solutions. I'm going to move quickly through this. The obvious one is, I've got a database, there's too much data. It literally doesn't fit in a database. It's unlikely that's because of disk size these days, but it might be like, your database just doesn't have enough RAM to keep the working set in one database. You've got to split it onto multiple. It might not have enough CPU, et cetera, et cetera. Another one is, you saw that some of those circles on my imaginary workload diagram, bigger than others, something that I bump into again and again is I've got a pretty homogeneous workload except for this one customer that keeps on sending big workloads and causing problems for everybody else. Another one is migrations. When you've only got one type of, when you've only got one shard, running operations on that shard, like schema migrations, it can be absolutely terrifying because if it goes wrong, it introduces a big latency regression or whatever, you're in big trouble. You've taken down the whole workload. Another variation of that is that team A has broken the database and team B is really upset about it. This very often happens because team incentives aren't aligned correctly. Team A might be more of a move fast and break things type team, which is totally fine. There's a place for that. Team B might be operating like a core function. So co-locating their systems can be very dangerous. Another one's locality. This is genuinely a sharding problem where you've got a lot of workers in one region, but a lot of customers in another region. And because you're serving one from the other, they have to obviously move across the Atlantic in order to use your system. It's very slow. One of the final ones is cost. Like, I know that I mentioned that sharded systems can cost more than unsharded systems, but sometimes, or a small number of shards, sometimes in order to support the workloads in an unsharded system, you have to provision absolutely massive shards or unsharded databases just to support the load at all, to ride over the bumps, whereas splitting that up into smaller pieces can actually be cheaper sometimes. Also flexibility. Sometimes when you have a sharded system, like a very naively sharded system, it's very hard to change. And so one of the things that I want to talk about today is how do you build a sharded system in such a way that you can modify it over time in order to like navigate through that diagram, rather than, again, just plotting your destination. So how do we actually shard these workloads? This is a really quick crash course. We usually use existing software in order to do this, like Vitesse or Cockroach. But like I mentioned, it's important to know how it works behind the scenes because just migrate to Vitesse is not a great solution at all. The key here is shard keys. Everything really comes down to this. So if you imagine an incoming workload, like say you're running a database service like I do, you might have a SQL query coming in, select email from users, etc. Now, I've highlighted here that the default shard key that you might consider is the user ID. Like there's something, you can identify every different workload based on the user ID, and this is a very common pattern. But it might not be the case. It's not the only way to shard these systems. You've also got users. Now users is a table in here. It might be a collection in Mongo. But you can imagine that you could take all of the different tables in your system and slice up the workload based on which table it's addressed to. And also, you've got the column in here. I think Charity mentioned earlier that you should move all of your metrics to a column, a store, and it's great advice because a lot of the time you do have an individual table, but you have a lot of different types of data in that table, and you can tease those things apart based on what type of data people are actually requesting. Another example here is if you're working closer to the edge on like a load balancer, then you might be able to use, I said foo here, which is a little bit unclear, but you might be able to use some subdomain, like a customer-based subdomain or a region-based subdomain in order to categorize this data and then forward it to the right database. Similarly, you might, after a user has logged in, you might have a cookie that has their user ID, something like this. You can interpret this at the load balancer side and then forward the data to the right place, or forward the request to the right place based on this user ID. What this basically comes down to is a function. You have an incoming payload of any kind, and you need to turn that into a shard key. So, for example, another of these SQL queries, your function might translate this insert query into the number 1234. That is your shard key in this particular case. You might also, I'm not going to talk about this too much today, but you might not have one shard key. You might have hierarchical shard keys, where one piece of data narrows down the search space a little bit, but it doesn't completely eliminate it. You've still got to provide another shard key in order to really zero in on that database. After that, after you've got your shard key, we have the shard mapping. Now, shard mapping, it's another function that takes a key, and it also takes a config, so it's the output of that first function. I'm not going to put too much code on the screen here, but here's a little Python, a little pseudocode. It's really the simplest way to shard things is just to do a lookup. In one of the previous examples I had, foo might be your shard key. In a lot of cases, if you've got a very small number of shard keys, you can really just have a dictionary that says foo goes over here into this database and bar goes over there into this database. Basically, the workflow looks like this inside of your system. So you have the blue blob being a workload coming in. You extract the key from it. Might be foo. You look it up in your table and then you forward it to the correct database based on what you found. So the user is kind of telling you what shard. They don't know exactly, they don't know the internal names, but they're telling you which shard it's going to go to. The more advanced option, one that we probably see most in databases, is a hash-based sharding, where you might take that shard key and then you might hash it based on the number of shards that you have, and then forward the request to the database or to the workers based on that. So in this example, you might say extract the key, you hash it, and then in here, because we have 4 shards, this comes out of the config, number of shards, you might mod for it. And so if you assume that your hash function works really well and hashes all of your keys into equal-sized buckets, you've now got 4 databases instead of 1 database, where they're all about the same size. This is tricky because it does assume that your hash is effective and it distributes the load across the key space. That's rare in my experience, which is why we very often use range-based sharding. And this is the last variation I'll talk about. A little bit more Python here. I hope this makes it clearer, not more obscure. But range-based sharding has 2 steps. First, you want to take your key and then cast it into the key space and figure out which range of keys it's in. And I'm going to illustrate this in a second because I know it's a little unclear. Then you want to take that range and you want to map that into a shard. So each range is hosted on one of these shards. Now, I've got a diagram here. I know it's a little unclear if you're not already familiar with range-based sharding. So you take your key, you translate it, you look up which range it is in, and then you look up which shard, your individual range is hosted on. And it looks something like this in practice. This is a key space, illustration of your key space. So you have negative infinity on the left, positive infinity on the right. Whatever your key is, it's going to fall somewhere into this key space, into this range of keys. And here, in this example, you've got one range, which is running on shard 1. Operationally, we might then split this key space into 2 ranges. So now you've got a range 2, which is from negative infinity to, say, 4 million. All of the keys that fall into that range are going to be put on shard 1. All of the keys into range 3 are going to be put on shard 2. And you can keep on subdividing your workload from there. I'll get into the specifics of how you might do this in a second. And in future, you can keep on dividing it and dividing it up. Now, the reason this is better than hash-based sharding is that you can see a lot of the key space here is on shard 2. And a small amount is on shard, 1. This is because the load tends not to be distributed evenly across the key space. It's depending on where the load is, like say you've got a customer that's especially busy, they might end up in range 5 and running on their own database. There are a few different ways that you can use these shard keys. Like I've illustrated single shard lookup here in all of these examples, but I do want to call out that sometimes you might have to send a request to all of your shards because you don't know which shard it's on. If you're doing like a select star from users for some reason, you don't know, and well, actually you do know that you're going to have to search all of the shards, so you do what's called a fan out. Other times you might want to do sub-sharding when you know that the data that you're looking for is in one of these shards, but you don't exactly know which, so you fan out and find it. I'm not going to talk too much about that. So here are a few patterns that I use, sort of abstract patterns that I use to pick how I'm going to break down systems into component parts. And I've seen all of these over the years. The first one is minor versus major sharding. Now, I want to clarify these are two categories of problems. Minor, or solutions, I suppose. Minor sharding, it tends to involve homogeneous resources, like databases of the same size, which are managed or orchestrated as a single unit. So you might have a CockroachDB cluster, for example, that has a whole bunch of nodes inside of it. That's minor sharding because somebody else is encapsulating the sharding for you. It might be a Cassandra, it might be a Kafka cluster where a topic is broken down into partitions, or it might be your own homebrew database like Stripe does. Because it's a single conceptual system, it's usually optimized, it's pretty easy to operate, and it has a lot of neat features like shard rebalancing, distributed transactions where your coordinator can send requests to all of your shards at once. That doesn't mean that you're free to just turn off your brain and throw everything in a Cassandra cluster. You still got to think about how the sharding works, like what your sharding keys are. Otherwise, so many of your requests are going to end up hitting so many of your nodes, and performance is going to be terrible. But it is a bit simpler if you can get to it. Major sharding, on the other hand, I've got some examples of how this might look here. It tends to involve totally separate infrastructure, totally separate resources, like say an RDS database, like an Aurora database in each of your shards. Now there's no coordinator across those, like moving data from one Aurora to another Aurora, you're kind of on your own. You've got to figure that out. Cellular architecture is another example of this, where a customer gets put into a cell and they are never leaving that cell, not without a whole lot of orchestration. So the first pattern, the first minor sharding pattern here is worker pools. They are usually stateless. Usually you'll use fixed or hash sharding because you're not worrying about database. Here, all you're doing is taking one pool and you're breaking it into multiple pools. So you see here, you have a pool of workers. All of your work is getting sent into those workers, and you can scale out those workers to provide more capacity, but you're still sending all of the work, spreading it to all of the workers. And that's a problem if some of the work is a very different shape or is more explosive than some of the other workers. It increases your blast radius in a lot of ways. And if you're unsharded, even if you have a lot of workers, it means your blast radius is basically total. So the very first pattern, the very first thing that I often do when I'm looking into these problems is split it out using subpools. So instead of having one gigantic pool of workers, you might have two pools of workers. And you can scale those individually, and it really, because they're stateless, it doesn't really matter what type of sharding you use as long as you can break your workload into two separate pools. Another pattern, which is really simple and I reach for fast, is read replicas. For stateful services, because it's not like worker pools, you can't just break up the workload and send it to a bunch of different pools. It's impossible to just take one database and break it in half. It's not impossible, but it's pretty hard work. What you can do though is separate, you can shard based on the type of workload, the read load or the write workload. And that's especially useful because the read load tends to be a lot bigger in most systems than the write load. So you can categorize the workload based on reads or writes. You can set up read replication, which you should be doing anyway. A lot of databases, they support streaming replication. You need that for failover. So in order for a new database to become available when the old one fails, you've got to have a hot standby ready. I'm sure a lot of you are doing this already, but a lot of the time I find that those hot standbys, they're not actually serving any queries. So one of the things you can do to shard data is to shard your data essentially, shard your requests into reads and writes, and then send the writes to your read replicas and the writes to your primary. You can scale a long way doing just this, and it's a really simple way as well. There are some consistency footguns you've got to be aware of here, you've got to think about, but we don't really have time to get into them here today. Horizontal sharding is probably, this is the most oversimplified slide in this entire deck. Very often, you'll take a data set, it'll be a table of users, for example, and you are going to want half of your users to be on one shard and half of your users to be on another shard. Customer ID is one that I reach for a lot because it's so ubiquitous. We probably all have a whole lot of different customers, and you can use that to duplicate basically everything about the database. You have all the same tables on both of the shards, but you can split which queries are sent to which database using something like the customer ID. Very often for this type of approach, we use hash-based sharding or range-based sharding. We very rarely use fixed sharding for this, except in the very special case where we have a very special customer and want to move them out to their own shard. So those are the minor sharding patterns. Here are some major sharding patterns which fit more into like a separate database type of model. First one here is vertical sharding. Now, this is exactly the same like diagram as the horizontal sharding, but in this case, it's actually not that much of a simplification. So if you, like I mentioned earlier, if you have a workload which has a whole load of rows, a whole lot of different customers, it's inconvenient to want to split those onto separate databases. It's a lot harder. You've got to do distributed queries and all of that. But in many cases, you've got, say, a users table, you've got a payments table, you've got an accounts table, all of this. Vertical sharding means that you can take some of those different categories of work, like say, take a whole different table and move that to a separate shard. So now queries to your users table can go over here, queries to your payments table can go over here. And it's really nice for users, well, sorry, not the users, I guess, the developers, because they don't have to change a lot. You can mostly organize this at the operations level and like send their queries to a separate database and increase the capacity that way. Probably the most common form of major sharding is a cellular architecture. Most systems, whether they're using cells or not, they sort of have one, just like regions, they have one cell by default. It's the whole world. So all of your workflows go through all of your workers and then they go straight to your one database. With a cellular architecture, you want to duplicate the entire world. And this is a lot of infrastructure. This is a lot more work than something like vertical sharding, because it means you're not just configuring like one component of your system twice, you're configuring your whole system twice, or like a big subset of your system twice. But this is it's a really nice model because it allows your system to fail in like smaller parts. Even with quite well-sharded internal systems, there's always the risk of a total regional or even global outage. The way that you get away from that total risk is basically having two separate systems which are not correlated at all. A special case of cellular architecture is multi-region. A lot of companies, honestly an embarrassing amount, run all of their infrastructure in one region. It's like having one cell. And even if you're pretty well sharded internally, you still run the risk of like, what if this region has a problem? Like they do have problems sometimes. What if one of our internal users applies a Terraform plan that like breaks the account in this region? I've seen it all with single regions, and whatever you do inside of a single region, there's always going to be the risk of everything breaking at the same time. So multi-region, you implement it the same way. Rather than having one, you have two. Multi-cloud is another example, which I'm not going to talk about today, other than to say beware of multi-cloud. It is not as simple as you think it's going to be. I would hazard a guess that like multi-cloud is probably 10 times more difficult than multi-region alone. Multi-region is great because it's hard enough to do multi-region, but you can at least assume the same software is going to work the same way in multiple regions. Multi-cloud, not the case. But if you really want to, it does offer a level of resilience that like you basically can't get anywhere else than having your system running in two totally separate cloud vendors. So now the final part of the talk, which is the paved road. I've showed like a lot of different simple explanations of like the different sharding patterns that I use. But more often than not, like your systems are quite grungy and like they already have a bit of sharding inside of them. There are many systems calling other systems. It's very rarely one box pointing to another box, right? So the first place that I look for in any system is like, can we introduce read replicas here? This is my favorite type of sharding and it's so underused. So I've drawn like a little diagram, like an imaginary system. I know that your systems are a little bit more complex than this, but you can imagine you got a load balancer, you got some workers, and you got a database behind that. So you got to have replication for availability anyway. And so one of the first things I like to do with these systems is look at the incoming workload and say, how much of this could we offload? Like, can we just put some of this on read replicas? And sometimes you got consistency questions, but 9 times out of 10, like 60 or 80% of your traffic coming in is reads. It's like serving it out of a cache, except it's a real database, so you don't need to build anything else. If you have read replicas, you can just start sending the queries to them. Frameworks like Rails and Django and like all of the popular ones, showing my age a little bit there by referring to those two, make it really easy. You can insert like an interceptor before your database queries, and they will just multiplex it to your read replicas. It's a piece of cake, and it can give you a lot of headroom as well. The next couple of steps really depends on whether your system is architected as a monolith or a swarm of microservices. I really tried to make like one distinct path, but it's hard, and it does depend. This is a big enough difference between systems that you've got to follow it either way. So with monolith, one of the techniques I really like is priority tiers. And this is a special case of sharding your workers. Like, you don't need to separate the database at this point, but if you have 2 separate pools of workers, not just one, you've now got 2 copies of your monolith running. And you can sort of play with that to put different types of traffic through the different worker pools based on what it is. So, for example, you might have like payments. This is how we do it at Stripe. You might have payments go through their own worker pool. There's nothing different about this worker pool other than we care about it very, very much. And so we don't touch it unless we're really sure. And then you have batch jobs, for example, which, I mean, we care about them, but like if they get broken for 5 minutes, it literally makes no difference. You just run them in 5 minutes and it's fine. So if we're doing a rollout or something like that, you bet we roll out the new version of the monolith to the batch job partition first before we roll out to the payment partition. And this applies very broadly. A lot of people can adopt this. So the way that you basically do it is by identifying the traffic. You've got to categorize the traffic in some way. Here, I've categorized it as an example using like important traffic with the crown and not so important traffic. Now, I know it's not that simple in reality, but there's usually some way that you can categorize. This is really important, this is less important. So you basically take those worker pools and you dedicate one of them to the important traffic, and less important traffic goes somewhere else. You do have to modify your load balancer in order to do this. It's got to be able to run that hash function from earlier on and say which of these worker pools it's going to, but that's fairly simple compared to something like range-based sharding, which is a lot more complex. And you can see here, we're sending the queries. The next step for a monolith that I've found really helps is going cellular. People always imagine going cellular as like a really complex thing, and it is. If you're running a very complex infrastructure, you've got to copy and paste so much infrastructure. But one of the nice things about monoliths is they're actually really simple. Like, there's a little bit of infrastructure, and all the complexity is inside the monolith. So I found that it's remarkably simple to just take the monolith that you have right now and start splitting it up. Like, the difference here is just that we've added a separate load balancer. It is incremental. You can't just split all of your infrastructure on day one. But if you start by splitting your load balancers up, you can quite soon advance to splitting up the entire thing. And so you identify each of the different stages along the way and split each of those so they're in separate pools. And you'll see there's no arrows between these different, what I'm calling cells here. And eventually we can start thinking about them as totally separate entities. And of course, once you've got 2 cells, I mean, the first one you're probably going to copy paste, but you're probably on your way to templating your infrastructure with CloudFormation, Terraform, or whatever. So standing up additional cells is hopefully not that outrageously difficult, especially if they're in the same region already. And this is a great way to scale your monoliths. You can go a long way with this. Microservices, on the other hand, some of the systems I've worked on, an increasing number these days are microservices, and the path is a little bit different there. Just going back to this previous diagram, I'm going to make a little bit of space here. You see I'm combining my read replicas into one. You should still do it. That should still be the first step. I just need to make space for the microservices. I'm also showing 4 here because just showing 2, it doesn't really illustrate what I'm talking about. The first step is you'll probably agree that, like, if you have a whole cluster of microservices, duplicating the whole thing it's somewhat, I mean, it's quite tricky. But a lot of the microservices I've seen, they're actually sharing a database behind the scenes. This runs counter to a lot of people's intuition about microservices. Most people would say your microservices should encapsulate their database like this. And that is true. I agree with that, because a lot of the workloads that you run in microservices, they are disjoint. So if you've got a payments and you've got authorization, like they're probably referring to two different tables anyway. So splitting these two things up can give you a lot of headroom, because now you can scale them individually. The next one you're going to find on microservices is horizontal sharding, because even if you split these up, what you're probably going to find is that one of your databases is like outsized compared to the rest. Usually I think every microservice swarm that I've seen has a whole bunch of little databases that you don't really need to shard at all. Like, you can get pretty big on sharded database these days. And then there's one which is bursting to the gills, which is going to melt down, and also usually is the most critical one. So at this point, it's time to replace that database with something which is sharded and distributed. What kind of database that is, I'm not going to try and tell you. It really depends on the type of system that you're running. It's plausible to like build your own thing, and if you can identify a really clean sharding key that never changes, maybe that's the right choice for you. But I've got to warn you, it's really complex, and I try and avoid it if you can. The best path here is to adopt something which is well established, like CockroachDB or UgiByteDB, if you're able to, or if you're in a real rush, you've got a MySQL there, you might want to put a Vitess on top of it, because that's the smallest incremental step. Still a pretty big step, but we're getting quite far into the path here, so you should be ready for that. If you're running a bunch of Postgres's, maybe you want to run Citus on top of it. If you've got a Mongo, you might want to put MongoS on top of it, because these run on top of your existing databases. Or you might want to migrate to something totally different, like DynamoDB. This is the time to do it if you're going to, because it just gets harder and harder. Though, if you were going to do that, you might have done it from the start. So to recap, here are our two diagrams. They're very different. The monolith scales in a different way to the microservice, but at this point you might notice that like you've got basically the same number of databases at the bottom of the thing. And that's because the data is the same. Whatever your architecture is, you've got the same amount of data, it's just sliced up in a different way. And that's the same for your code base as well. It's all in the monolith or it's sliced up into the microservice. The next step after this, and I'm just wrapping up because I'm just at 35 minutes now. The next step after this is multi-region. If you're getting to this stage and you're still in a single region, I'm not going to point any fingers, but like it's the risk of regional failure at this point is getting pretty real. If you're running like tens or potentially hundreds of shards inside of a region, you're going to have a really bad day when that region becomes degraded. So you want to start thinking about how am I going to get this system into multiple regions. For the monolith, it's kind of easy because you've already done cellular architecture at this point. Ideally, and I know it doesn't work this way in practice, ideally you can just stand up a new cell that happens to be in a new region if you're in the same cloud vendor. Of course, that's often not the case, because when you try and do this, what I've found actually every time is that there are some things in that existing region that happen to be cross-sell, like some security groups or like something like a VPC that somebody clicked around and set up manually 10 years ago. So this step can be a little tricky. You're standing up a new cell in a new region, but the actual work is like making that new region work at all. But at this point, it's well worth doing. For microservices, you could take the same approach. You could say, let's go cellular first so we can run multiple copies of our microservice swarm inside of a region. But in my experience, that's like 80% of the effort and a lot less benefit. What works quite a bit better actually is you just stand up a new region. You start with a new Kubernetes cluster, a new swarm, new service discovery, all of that inside of a second region, run a second copy of your microservice swarm, which again is already sliced up pretty finely, and you're pretty much good to go. That's a lot of headroom that you've granted yourself there. Now, at this point, once you're multi-region, maybe you're cellular, you've sharded your database, maybe you're running a distributed database, you obviously know what you're doing at this point. You could be serving millions of QPS, so it's hard for me to be prescriptive about what you should do next. If you've got major shards already, like cells, you're probably going to need, with your monolith, to start adopting minor sharding. You're probably going to need to introduce a distributed database, because all those unsharded databases, however many cells you have, they'll only take you so far. If you already have those minor shards, you're probably going to want to start splitting it up into cells. Sooner or later, you're going to need multiple copies of that microservice architecture inside of a region. But it really depends. The one thing which I haven't spoken about, but you are going to want to talk about at this stage, is regional failover. even if you're in 10 regions, at this point, scalability-wise, the risk of a region failing, it can be a huge reputational impact. Even if only that one region fails and you say, well, it was only 20% of our traffic, great, that can still be catastrophic. So you might want to start talking about regional failover, where individual cells cover multiple regions. It's pretty rare, but we're actually working on it right now at Stripe. This is the conclusion. I talked about a lot of problems here. I really like to use these categories of problems, isolation, blast radius, latency, and all of that, to think about like, how can workload sharding help? Like, is the problem I'm facing right now a workload sharding problem? Very often the answer is yes, actually it is, surprisingly so. There's a very small number of fairly simple patterns that I use in order to try and categorize these. Like, can I slice it vertically? Can I slice it horizontally? Like, can I take advantage of some other property of the system, like read replicas, to scale this a little bit further? And then putting all of those things together, one of the really big challenges is deciding what order to apply them in, because you can apply basically any of these patterns in any order. But some of them are more effective at a very big scale, some of them are more effective at a very small scale. Picking which one it's a matter of experience. That's basically it. That's the whole conclusion. So thank you very much for listening.